Welcome to the who, what, where, when, and why of exoplanets with me, Didier Queloz, astrophysicist and Nobel Prize winner. The first reason is the planet is a very tiny object next to something which is a monster, which is the sun. The sun is huge, it's big, the sun is shining. If you look at the sun, you're just almost blind. So imagine trying to look at a planet next to a star like a sun, just too much light. You don't see it, you're just completely blind. So looking at the planet is almost an impossible task. So the trick here is you don't look at it, you try to feel the planet by looking at the effect of the planet on the star. One of the effects of a planet on the star during the orbit is to shake a little bit the position of the star. And this change of motions, this shaking, we can detect it practically by measuring the change of velocity of the star. The velocity of the star, usually it's a constant value because all stars have a speed. But when there is something orbiting that star, the velocity will gently change up and down, wobble, going back and forth, and you can use that to find out that there is a planet. This is the technique that we use to find the first planet. So the effect of a planet is tiny, so it doesn't change the speed of the star that much. So it means that to detect this tiny change, you need to develop extremely specific machine that we call spectrograph to detect these tiny motions. And this is difficult. It took a long time to develop the technology and the techniques to do that. It's a very difficult question, I must admit. The only example of planet where there is life right now is Earth. And it's not very clear whether life was possible and has been possible on other planets of the solar system like Mars, for example, or Venus. So usually what people imagine is if you have a rocky planet with water and an atmosphere, there is a chance that you will develop life. No, practically, we have to show it because science is not about just idea, it's about facts. And then the big question is, what should we be looking for? We know life is changing the chemistry of things. The carbon that we have on the planet Earth right now is transformed by life. You can imagine that other elements has been changed or modified slightly by the fact it's being processed by life. When you look at the planet and you look at the atmosphere, maybe by looking in the detail what is the molecular compositions of this atmosphere, you can guess that there is life ongoing on that planet. And that's how we're going to work in the next 50 years, and I'm pretty sure we will have a lot of surprises. I discovered Didier Queloz and my professor Michel Mayor, the first exoplanet. And it's a fascinating story because it was not exactly expected to happen like that. My PhD work was to design a machine, a new kind of machine, and produce also the global analysis of this machine that could detect a planet on other stars. So, fair game, machine was built, I did a good job, the machine could detect, I think had the capability to detect it, but at that moment, 30 years ago, everybody was thinking about planets like the solar system. And the biggest planet of the solar system that we were aiming at detecting was Jupiter. Well, the challenge is Jupiter takes 10 years, more than 10 years to orbit this star. So the program to detect Jupiter is essentially to keep observing stars for 10 years and to look at a gradual change of the speed of the star. Well, I started the program. Nobody, my professor or myself, were expecting anything. And the more I was observing the star, the less it made sense because the data keep moving up and down. And I say, wow, what's really going on there? I mean, it doesn't make sense. And at the moment, my brain can switch. I say, well, maybe there are some systematics here. I should try to find out. And I worked at finding what everybody would do, as I expect, is looking for periodicity into the data. And I found out that there is some periodicity into the data, which is a bit more than 4 days. At that moment, I realized, well, it seems to have a very clear signal. It's 4 days. What about if it's a planet? And I computed the mass of planet that would produce this signal, and I came up with half a Jupiter mass. And I said, well, maybe it's a planet. And I sent a fax at that time to my professor. He was in Hawaii still. I said, well, Michel, I think I found a planet. And Michel really said, okay, maybe. I don't think he believed me at that time. Anyway, I said, wait, I'll be back and we just review what you've done. I think he didn't believe it. Fair game. I mean, who could he? Nobody was expecting this. And he came back, and then we looked at the data together. Again, I explained all what I did, and he said, well, I have to admit, I don't see any other explanations at that moment. But it's impossible. So we decided to just let it go and wait for the star to be back to reobserve the star 4 months later. I came back in July in 95, and then we observed the stars. And at that moment, I had my model, the predictions of the planet, and we were on the telescope. And every night it was like a dream. And it's like in the books, you have the data been recorded, your predictions, and bang, it's exactly what you expect. The first night, bang, exactly the right value. And we say, okay, it's a piece of luck, can happen. So let's do the next night. Second night, there is a change of velocity, bang, still on the expectations. I say, it looks good, but well, 2 is not enough. I mean, let's do a third one. Third night, again, exactly on the curve. And at that moment we say, okay, well, it's likely to be right, but let's be really, really safe and secure, because we were so uncertain about all that stuff. So maybe it's the fact being Swiss here. We waited the 4th data point, in addition to all the other that I had already collected, to say, okay, no, I think we have it. And then started the complications, because at that moment we started to understand we had to face a big problem, is to convince the rest of the community, because it took us so long to be convinced by ourselves. So how the community would react. And we prepared the paper. It was really a struggle to get this paper published. And when we made the announcement later in October, frankly, very few people believe about that planet. I think there was a lot of skepticism. It was so bizarre. Very few, I think, scientists understood that there was something really interesting here. And I must admit, it was not easy for me. So I just had my PhD and I was a junior scientist. I did a major discovery. I was convinced about that, but nobody believed in that stuff. So it lasted for 4 years. During 4 years, the community was very skeptical until the first transit. So planet was detected at the moment they were crossing the stars. And at that moment, I think the community realized, oh, okay, if there's a transit, there's also the radio velocity signals, both techniques, both technology, telling the same story, then all this planet must be real. At that moment, the field kind of started, because people realized that we really are facing something new here. That's kind of a long story to explain that when you do something which is dramatically new, that nobody called a revolution, really. This new detection are kind of a revolution, because it tells us the story that the solar system is different from most of the majority of the planet in the galaxy. It's not something that will be an easy ride, the story of the first discovery of the first exoplanet. Morning. Comedy. Ooh, difficult. I don't know. I like both.